Good morning, I am Seema from BSc Chemistry Honors Final Year, roll number 62. This video is especially for the visually impaired students. We are going to study the chapter of the organic chemistry, organometallic compounds. That starts introduction. Organic compounds in which a metal atom is linked directly to a carbon atom are called organometallic compounds. A large number of the metals, example lithium, sodium, magnesium, zinc, mercury, lead, cadmium, etc., form such compounds. The organic part is generally an alkyl or aryl group. They are named simply by the adding the name of the metal to the name of the organic group linked to the metal. For example, methyl lithium, ethyl magnesium, n-butyl lithium, diethyl mercury, tetraethyl lead, phenyl lithium, dimethyl cadmium, diethyl zinc. The carbon metal bond in the organometallic compounds differs widely, varying from bonds which are essential ionic to those which are largely covalent. Thus, the extent of the ionic or the polar character of the bond is largely determined by the electropositive nature of the metal. More electropositive the metal, more is the ionic character of the carbon metal bond. In general, the ionic character of the carbon metal bond follows the sequence. The reactivity of the organometallic compounds also depends upon the nature of the carbon metal bond. Generally, the larger the ionic character of the carbon metal bond, the more reactive is the organometallic compound. However, compounds having intermediate ionic character are of greater importance because of their lower reactivity and selective nature of their reactions. Organometallic compounds are extremely useful for the synthesis of a vast variety of the organic compounds. Apart from these, many of the organometallic compounds are commercially important as well. For example, tetraethyl lead is extensively employed as an anti-knock compound. Organtin compounds are used as antioxidants in rubber products. Phenylmercuric acetate is used as a fungicide and disinfectant, and organoarsenic compounds are used in the medicines. Organomagnesium compounds, Grignard reagent. Organomagnesium halides are extremely important reagent in synthetic organic chemistry. The reagents are commonly known as Grignard reagent after the name of the discoverer. Victor Grignard received the Nobel Prize in the chemistry in 1912 for their discovery. The general formula of the Grignard reagent in RMGX or ARMGX, where R represents the alkyl or the argon represent AR represents any aryl group. Preparation. Grignard reagents are prepared in the laboratory by the action of an alkyl or aryl halide, preferably bromide or iodide, on magnesium metal. Alkyl halide react with the magnesium in the presence of dry ether, give rise to the Grignard reagent. Besides ethyl tetrahydrofuran, dioxane, dimethoxyethane, or dimethyl ether of diethylene glycol, tertiary amines, etc., can also be used as the solvent. In fact, THF is considered to be the solvent since it increases the reactivity of an alkyl or aryl halide towards the magnesium. It is because of the reason that the Grignard reagents of less reactive aryl and the vinyl halides, which are difficult to prepare, are prepared in the THF. Further, it has been found that for a given alkyl group, the ease of the formation of Grignard reagent is the order of iodine, bromide, and chloride. The alkyl or aryl magnesium fluorides are, however, unknown. For a given halogen atom, the order of reactivity is CH3x greater than C2H5x greater than C3H7x. That is, the formation of Grignard reagent becomes increasingly difficult with increase in the number of the carbon atoms in the alkyl group. The use of the tertiary alkyl iodides is avoided since they readily lose a molecule of the hydrogen iodide to form an alkene. Tertiary alkyl chlorides may be used. Procedure for the preparation of the Grignard reagent. Alkyl or aryl halides is added slowly to a perfectly clean and dry flask containing dry magnesium turnip covered by a layer of the absolutely dry ether or THF. The reaction mixture is warmed a little when an exothermic reaction should soon start. If the reaction does not start within 5 minutes, a few crystals of the iodine are added and the reaction mixture is warmed a little. Vigorous reaction soon sets in and magnesium gradually dissolves, forming a cloud solutions of the Grignard reagent. Precautions in the preparation of the Grignard reagent. During the preparation of Grignard reagents, the following precautions must be observed. The apparatus should be perfectly dry and protected from moisture by using a calcium chloride guard tube. All the reagents and the solvents, that is alkyl or allyl halide, magnesium metal and the ether, must be absolutely. Ether used as a solvent must be completely free from the alcohol. This can be done by the first washing ether several times with water, followed by drying over anhydrous calcium chloride for 1-2 days, and subsequent distillations over the sodium and atmosphere of the dry nitrogen free from the oxygen and carbon dioxide should be maintained throughout the course of the reaction. These precautions are necessary since Grignard reagents are decomposed by the moisture and react with the oxygen and carbon dioxide to form the alcohol and carboxylic acid respectively. The ethereal solution of the Grignard reagent thus obtained is generally used as such for various reactions by adding to it to the other reagent. Mechanism. The mechanism of the formation of Grignard reagent is still not certain. According to Combark and Beckmann, the reaction commences with the formation of a small amount of magnesium halide and then proceeds by a free radical reaction. The mechanism also elegantly explains the initiating effect of the iodine, which may be ascribed to the formation of the magnesium iodide from the magnesium and the iodine. Structure of the Grignard reagent. The structure of the Grignard reagent has not been finally settled so far. The recent research has shown that the actual structure varies with the particular Grignard reagent and the solvent used for its preparation. Grignard and Blaise observed that the evaporation of the ethereal solution of the Grignard reagent resulted in a white solid having the composition RMgX2C2H52O. They suggested that ether molecules were present as the ether of crystallization. X-ray analysis of these dietherates suggests that the four groups are arranged tetrahedrally. The formula suggests that ether does not merely provide a medium for the reaction, but it also helps to dissolve the Grignard reagent formed during the solvation by the ether molecules. This is supported by the observation that the Grignard reagent can be prepared even in the benzene solution in the presence of a tertiary amine, which coordinates with the magnesium like ether and thus dissolves it. Further formula show the Grignard reagent in the monomeric form, but physical studies has revealed that the Grignard reagent exists as one complex of a dialkyl or diaryl magnesium and magnesium halide coordinated with the molecules of ether. These two species are held together by halogen bridge. However, for the sake of convenience, the formula RMgX has been used to represent the alkyl magnesium halides in the text. Reactions of the Grignard reagent. The carbon-magnesium bond in Grignard reagent is highly polar due to the large electronegativity difference between the carbon and the magnesium. Consequently, due to greater electron density around the carbon, the alkyl group in the Grignard reagent acts as a carbanion or a nucleophile, that is, it can attack any electron deficient center in other molecules. Other words, Grignard reagents chiefly undergo the nucleophilic substitution or nucleophilic addition reaction. Nucleophilic substitution reactions. Grignard reagents react with the compounds containing an hydrogen or halogen atom. All such reactions involve the nucleophilic attack of the alkyl group of the Grignard reagent on the electron deficient center. Nucleophilic Nucleophilic addition reactions. Grignard reagents react with the compounds having a multiple bond such as carbon double bond oxygens etc. to form the addition products which when hydrolyzed yield a variety of the compounds. In all such reactions, the addition of the nucleophilic group of the RMgX, that is R negative, occurs at the more electropositive and that of magnesium MgX group at the more electronegative atom of the multiple bonds. Synthetic uses of Grignard reagents. Grignard reagent serves as extremely valuable starting material for the synthesis of a vast variety of the organic compounds. They have attained a position in the synthetic organic chemistry unrevealed by other class of the compounds. To illustrate this, some important synthetic applications of the Grignard reagents are described below. First is the alkenes. By the action with the active hydrogen containing compounds, active hydrogen containing compounds such as water, alcohol, thioalcohol, carboxylic acid, hydrogen sulfide, ammonia, amines, tertiary, secondary, but not the primaries and secondary, but not the tertiary terminal alkynes react with the Grignard reagent to form and nitrate, a alkane corresponding to the alkyl or the aryl group of the Grignard reagents. Since methane is evolved quantitatively when CS3-MgI is treated with the compounds containing the active hydrogen, therefore these reactions can be used for the estimation of the OH, NH2, SH groups in the organic compounds. The method applied is called Jerry Winton's methods. Aryl magnesium halides also behaves as in the similar manners. By the action with the reactive alkylides, Grignard reagent react with the alkyl halides such as tertiary butyl chloride, benzyl chloride to forms the alkanes. Second point is alkenes. Grignard reagent weak nucleophile do not react with the simple alkyl halides. However, compounds containing more reactive halogens such as the allyl iodide react with them, giving the alkynes. Grignard reagent react with the terminal alkynes, forming the alkynyl Grignard reagents. Depends upon the treatment with the alkyl halide give the higher alkynes. Primary alcohols. By the action with the ethylene oxide followed by the hydrolysis. Grignard reagent with the ethylene oxides to form the additions products which on hydrolysis with the dilute hydrochloric acid forms the primary alcohol containing the two carbon atoms or more than the alkyl halide. By the action with the formaldehyde followed by the acid hydrolysis. When treated with the formaldehyde, Grignard reagent forms an adduct which on hydrolysis with the dilute hydrochloric acids gives a primary alcohol. By the action with the oxygen, primary alcohol are formed by passing dry oxygen through the solution of a Grignard reagent followed by the acid hydrolysis of the resulting the addition product. Secondary alcohol by the action with the aldehyde other than formaldehyde followed by the acid hydrolysis. Grignard reagent first reacts with the ethyl formate to form an aldehyde, which in turn reacts with another molecule of the Grignard reagent to the yield an adduct, which forms a secondary alcohol on the hydrolysis. Tertiary alcohol by the action with the ketones followed by the hydrolysis. When the ketones with the Grignard reagent and then hydrolysis, then it gives the tertiary alcohol. A tertiary alcohol having at least two similar alkyl groups may be prepared by the interacting between an ester other than formic ester and excess of Grignard reagent. Reactions will be taken into the two steps. By the reaction with the acid chlorides and the anhydrides, Grignard reagents react with the acid chlorides or anhydrides products which depend upon the acid hydrolysis gives the tertiary alcohol. The reaction also takes place into the two steps. Ethers. Grignard reagent react with the lower halogenated ethers to yield the higher ethers. Aldehyde. When a Grignard reagent is treated with the ethyl formate, an aldehyde is formed. However, with the excess of the Grignard reagent, the product obtained is a secondary alcohol. Aldehyde are obtained in a better yield if ethyl orthoformate is employed instead of ethyl formate. This is so since the formation of acetal in this case prevents the formation of the secondary alcohol. Aldehyde may also be obtained by the interactions between a Grignard reagent and a hydrogen cyanide followed by the hydrolysis of the adduct formed ketones by the treatment with the alkyl cyanides followed by the acid hydrolysis. The next is the by the action with the acid chlorides. It discussed that equimolar amounts of a Grignard reagent and an acid chloride gives an additional product which forms the ketone on hydrolysis. If Grignard reagent is used in excess, tertiary alcohols are obtained as the ultimate products of the reaction. Monocarboxylic acid. Grignard reagents interact with the dry ice to form the addition products which on acid hydrolysis gives the monocarboxylic acid esters. By the action with the ethyl chloroformate, equimolar amounts of a Grignard reagent and ethyl chloroformate react together to form the higher esters. Thioalcohol. Grignard reagents reacts with the sulfur to give an addition product which gives a thioalcohol on the hydrolysis. Phenols. Aryl magnesium halides reacts with the oxygen to form the addition product which depend upon the hydrolysis gives the phenols alkyl cyanides by the interactions of the Grignard reagent and cyanogen chloride or the cyanogen. Excess of Grignard reagent is avoided since it will react further with alkyl cyanides to yield the ketones. Primary amines. Grignard reagent react with the chloramine to forms the primary amines. Responsible yields of the primary amines is obtained only with the Grignard reagents containing the tertiary alkyl groups. Primary amines can also be prepared in the satisfactory yields by the action of a Grignard reagent, chloride or bromide, but not the iodine on the orthomethyl hydroxyl amine. Sulfinic acids on passing sulfur dioxide into a well-cooled solution of the Grignard reagent, an addition product is obtained which on hydrolysis gives the sulfonic acid. Dithioic acids. These are prepared by the action of a Grignard reagent with the carbon disulfide followed by the acid hydrolysis. Organometallic compounds. Grignard reagents and inorganic halides interact with each other resulting in the formation of other organometallic compounds. Abnormal addition of the Grignard reagent. Addition to the hindered ketone if the Grignard reagent or ketone containing branching at the alpha carbons. Sometimes the usual addition reaction does not occur due to steric hindrance. Instead, reduction occurs in which a hydride ion is transferred from the Grignard reagent to the ketone via six-membered cyclic transition states in a manner similar to Marivane-Pondorf-Verlet reduction. For example, when isopropyl magnesium bromide is added to the diisopropyl ketone, the expected tertiary alcohol is not formed. Instead of the secondary alcohol, diisopropyl carbonyl is obtained by the reduction of the keto group. Addition to alpha beta unsaturated compounds. Alpha beta unsaturated carbonyl compounds react with the Grignard reagent to give the 1,2 addition across C double bond O bond and 1/4 additions. The orientation of the addition is often controlled by the steric factors. In general, substitutions at the carbonyl group favors the 1,4 addition, while substitution at the double bond favors the 1,2 additions. In most cases, both products are formed, but alpha-beta unsaturated aldehyde nearly always gives the exclusively 1,2 addition products when treated with the Grignard reagent. However, the extent of 1/4 addition of the Grignard reagent can be increased by carrying out the reactions in the presence of the cuprous chloride or cupric acetate, etc. This is called the conjugation addition and probably occurs by a free radical mechanism. Limitations of the Grignard synthesis. Grignard reagent suffers from the following limitations. The Grignard reagents are sensitive to the moisture, oxygen, and carbon dioxide and hence must be protected from them. This makes the handling of the Grignard reagent difficult. Grignard reagents cannot be prepared from alkyl halides containing other reactive functional groups such as OH, SH, NH2, etc. since they all are react with them. Only alkyl halides containing a few other groups such as R, OR, argon X, halogens X can be used to form the Grignard reagent. Generally, branching of the carbon chain near the functional group prevents reactions probably due to the steric hindrance. For example, Grignard reagent or CS3-MgBr or CS3-MgI does not react with the di-tertiary butyl ketone. Similarly, if Grignard reagent contains large alkyl groups, the reaction is sometimes prevented again due to the steric hindrance. For example, isopropyl methyl ketone reacts with the CS3-MgI but not with the tertiary butyl magnesium chloride. Compounds which are capable of enolizations liberate the hydrogen with the Grignard reagent. Nitro compounds cannot be used in Grignard synthesis since they oxidize the Grignard reagent. Despite the above limitations, Grignard reagents are still the most important tools in the organic synthesis. Organogen compounds. Although organogen compounds of the type R2ZN are not commonly used in organic synthesis, they are particularly used useful when the milder reagents are required. Methods of the formation. Following methods have been used for the preparation of organozinc compounds from alkyl halides. Alkyl iodides react with the zinc copper couple in high boiling ethers to form the alkyl zinc iodides, which upon the subsequent distillations in an atmosphere of CO2 undergo disproportionation of the to give dialkyl zinc compound from organoaluminium compounds. Treatment of trialkyl aluminium with the zinc chlorides gives the dialkyl zinc compounds. These methods form the basis of laboratory preparation of these compounds. Physical property. Dialkyl zinc compounds have linear geometry due to sp hybridization of the zinc atom. They are non-polar, low boiling liquids or low melting solids soluble in the organic solvents. The lower zinc compounds are highly inflammable in the air and hence are usually prepared and used under CO2 atmosphere. Chemical reactions. The chemical reactions of the organozinc compounds are similar to those of the Grignard reagent, which the only difference that they are less reactive. For example, they do not react with the CO2 and react only slowly with the cyanides, ketones, and esters. Some important chemical reactions of the dialkyl zinc compounds are discussed below. Reaction with the water. When they readily react with the water, forming the alkenes. Reaction with the alkyl halides. Dialkyl zinc compounds do not react with the primary and the secondary alkyl halides. They react with the tertiary alkyl halides to form the alkenes containing a quaternary carbon atom. Reactions with the acid chlorides. They react readily with the acid chlorides to form the ketones. Reformatsky reactions. When an aldehyde or a ketone is added to the solution of a alpha haloesters in the presence of zinc, an organozinc compound is first formed, which then adds to the carbonyl group in a manner similar to the Grignard reagent to form a beta hydroxyesters. This reaction is called Reformatsky reaction and is useful method for preparing the beta hydroxy esters, acids, and their derivatives. For examples, ethyl bromoacetates in the presence of dry ethers gives the organozinc compounds idomethylene zinc iodide. Idomethylene zinc iodide is an important organozinc compound and it is obtained by the action of zinc copper couple on the methylene iodine. It reacts with the olefins to form the cyclopropane derivative. This reaction is called Siemens-Smith reactions and is used for preparation of cyclopropane derivatives. The additions occurs in a stereospecific syn manner according to following concentrated mechanism. Organolithium compounds. Compounds in which lithium atom is directly bonded to a carbon atom are called organolithium compounds. Organolithium compounds are more reactive than the Grignard reagent and also undergo a few additional useful reactions. Therefore, they are widely used in the organic synthesis these days. Formation of alkyl lithiums by the reaction of an alkyl halide with the lithium. Alkyl lithiums are generally prepared by treating an alkyl halides with the lithium in the hexane, benzene, or any other hydrocarbon solvents at the low temperature in an inert atmosphere of the nitrogen or the argon. For the preparation of the alkyl lithium, hydrocarbon solvents are prepared over ether since the use of the ether not only encourages the Wood's reactions but also reacts with it. By the metal-metal exchange, alkyl lithiums can be readily prepared by the replacement of the one metal by the another. Chemical reactions of the alkyl lithiums. The carbon-lithium bond is more polar. Electronegative difference is 1.6 than the carbon-magnesium bond. Therefore, alkyl lithiums are more reactive than the Grignard reagent except a few difference. Their chemical behavior is similar to that of the Grignard reagents. Some of their important chemical reactions are: first is resemblance with the Grignard reagent. They resemble the Grignard reagent in most of their reactions. Some of these reactions are formation of the hydrocarbons. Like Grignard reagents, they react with the compounds containing the active hydrogen to form the corresponding hydrocarbons. Formation of primary, secondary, and tertiary alcohol. free alcohol by the action with the formaldehyde. Like Grignard reagents, alkyl lithium compounds also react with the ethylene oxide to form the primary alcohols containing the two carbon atoms more than the starting alkyl aryl halides. Secondary alcohol by the action with the aldehydes other than the formaldehyde. Tertiary alcohol by the actions with the ketones. Formation of ethers by the action with the monochloroethers. Formation of aldehyde by the action with the ethyl or ormate or hydrogen cyanide. Formation of ketones by the action with any orthoesters other than orthoformic esters or alkyl cyanides. Formation of nitriles by the action with the cyanosyl chloride. Reaction with the alkyl halides. Alkyl lithium reacts with the alkyl halides to form the alkanes. Reaction with the aryl halides. Aryl halides undergoes the nucleophilic substitution reactions by the elimination, addition, or benzene mechanism. Reactions with the heterocyclic compounds. Heterocyclic compounds undergoes the nucleophilic substitution reaction by molecular displacement mechanisms. Pyridine, when reacts with the benzene's lithium 383 Kelvin nucleophilic organometallic substitutions, give rise to the 2-phenyl pyridine quinoline in the presence of the lithium in the presence of the ethers to give the 2 and butyl quinoline difference from the Grignard reagents. Organolithium compounds being more reactive than the Grignard reagents undergo some additional reactions. Action first is the action with the carbon dioxide. Grignard reagents yields carboxylic acid with the carbon dioxide, while the organolithium compounds yield the ketones. Action with the carbon dioxide. Grignard reagents yield carboxylic acid with the carbon dioxide, while organolithium compounds yields the ketones. When carbon dioxide reacts in the presence of the hexanes, then the alkyl lithium attack on the carbon atoms, then an unstable product is formed, and this unstable product, when water molecules is lost, then the ketones formations takes place. This difference is due to the reason that organolithium compounds are more strongly nucleophilic than the Grignard reagents and thus reacts further with the intermediate responses stabilized carboxylate anion giving the cations. Action with the carboxylic acid. Alkyl lithium compounds react with the carboxylic acid yield ketones as the main product. Grignard reagent on the other hand give the alkanes or arenes corresponding to the alkyl or the aryl group of the Grignard reagent. When benzoic acid is reacts with the CH3Li or hexane, then the methane group eliminated here, and again CH3Li reacts with the group and unstable product is formed. When this unstable products water molecules is lost, then the acetophenone formations takes place. Addition to the carbon-carbon double bond. Unlike Grignard reagents, organolithium compounds add to simple alkenes to give a mixture of the compounds. The addition occurs at a high pressure 100 to 500 atmospheres. For examples, CH3Li plus ethene group react in the presence of the hexanes. Then, step by steps, this reaction takes place. Formation of the tertiary alcohol. Organolithium compounds being more nucleophilic and smaller in the size than the corresponding Grignard reagents and to sterically hindered ketones to form the sterically hindered tertiary alcohol. Grignard reagent, on the other hand, do not give such additions reactions. For example, isopropyl lithium adds to diisopropyl ketone to yield the triisopropyl carbinol. When isopropyl lithium plus diisopropyl ketones reacts in the presence of the dry or hexanes, then they give rise to the triisopropyl carbinol. In contrast, when the isopropyl magnesium bromide is added to the diisopropyl ketone, the expected tertiary alcohol is not formed. Instead, reduction of the ketone by the Grignard reagents occurs to give the diisopropyl carbinol and propylene. When reactions with the alpha beta unsaturated carbonyl compounds, organolithium compounds being more nucleophilic predominantly undergo the 1,2 addition to the alpha beta unsaturated carbonyl compounds, whereas Grignard reagents gives mainly 1,4 addition products. For example, when benzyl acetones reacts in the presence of hexane and the methyl lithium, then 1,2 addition product is the formed. When 1,2 addition product is formed when hydrolysis takes place, then the 2-methyl 4-phenyl but 3 in 2 ol product is formed. Benzyl acetones reacts with the Grignard reagent, then 1,4 addition product takes place, and when hydrolysis is done of the 1,4 addition product, then 4-phenyl pentane 2-on product is formed. Thank you.